There we are. Okay, so we now are recording, and it is May 2nd, 2019. We're doing our 110 Acoustics and Psychoacoustics review Zoom session. Now, there's the final exam. Do you know, can you tell me what date is are you taking the final exam? Is it proctored, or are you taking it online? Do you know that? Can one of you tell me?
It's unproctored.
Okay, so you get to take it as soon as it's released, right?
Correct.
I've looked at the exam as well. It has about 109 questions, 110 questions. I think they're each worth 2 points. And the exam is comprehensive. It starts at the beginning and goes all the way to the end. But most of the questions should be really about the latter half of the course, psychoacoustics. And I have a picture I've got, actually, I've printed up the exam, yeehaw, right in front of me here, okay? Big events. I just want to tell you the things you need to know, okay? This is what you need to be able to do. From the first half of the course, be sure that you know how to calculate period and frequency. Okay, so remember, way back, frequency is 1 over the period, period is 1 over the frequency. So if you're looking at 1,000 hertz, what's the time it takes for one cycle to take place over 1,000 for 1,000 hertz tone? 1 divided by 1,000. And you get, when you hit that, 0.001. Oh, 0.001 seconds. That's the length of time it takes to complete 1 condensation, 1 rarefaction. What's the period of a 500 hertz tone? 1 divided by 500. What do you get? 0.002 seconds. Okay? And if you had a question saying, what's the frequency of a sound that has a period of 0.002 seconds? Then you just do it the other way around. You go 1 divided by 0.002 equals 500. So make sure you have that pair of calculation equations down, okay? Because there are some questions on the final that have that. Another formula you need to know from the first half of the course is wavelength. Wavelength equals speed of sound over frequency. Frequency equals speed of sound over wavelength. Here's the trick. Speed of sound is always on the top. Okay? So if the speed of sound is 340 meters per second, okay, wavelength equals 340 meters per second divided by whatever the frequency. So let's pick an example. Wavelength. Excuse me, what's the wavelength of a 500 hertz tone? Well, speed of sound is 340 meters per second. So get my calculator out. Okay, look under the light here. 340 divided by 500 equals 0.068 meters, 0.68. That's what it is. Okay? And if it's asking you to calculate, what's the frequency? Frequency is speed of sound over wavelength. Wavelength is speed of sound over frequency. So this second pair of equations is talking about the length, the physical length of the wave. The first pair of equations was talking about what's the time on your watch. What time did it take for one wavelength to occur? The second pair of equations is asking you for what's the physical length? How long is that second? What's the length of it? Okay? So you got 2 pairs of equations. F is 1 over P, P is 1 over F. The second pair of equations is wavelength is speed of sound over frequency. Frequency is speed of sound over wavelength. You've got those down, have them memorized. When you encounter those questions on the final, you'll be able to just whip them off. Boom, bam, done. Well, what you drinking there, Julie? Has it got any booze in or what? Oh, I got this. I wonder what that is. Could be grape juice. Then again, wine.
No, I'm studying tonight. Can't be drinking.
You're what? You're what tonight?
I'm studying.
You're studying tonight. So when do you plan on taking your final?
I'll probably let my acoustics exam be my last exam.
Me
Get
too.
the other ones out of the way.
Yeah, why not? Here's your third equation you need to know. And you can guess what this one is. It's the decibel from hell. Okay? It's all about the decibel. So, what the hell is that decibel? Remember from the unit 2. What is 0 dB SPL? It's the softest it takes to hear a 1,000 hertz tone at 1 meter distance from a speaker with 2 ears, right? Remember that? Okay, so they played 1,000 hertz, they sat someone down in front of a speaker 1 meter away, and they measured the pressure against the eardrum that was required to just barely hear that tone. And that pressure happened to be 0.0002 dynes per centimeter squared against the eardrum. So they called that pressure 0 decibels sound pressure level. dBSPL, they'll call that 0. All other intensities are related to that ground. There's the ground, 20, 40, 60, 80, everything's related to that ground. Okay. So if you have some pressure against the eardrum that's more than 0.0002, what dBSPL would that be? Well, let's say you had a pressure of 0.002. So why don't I just draw it on a paper here? Through the review, I'm not even looking at any notes. I'm not looking at any PowerPoints. Forget that crap, okay? You know where to look in that. So what we're doing in this review is that we're just drawing the skeleton bones of what we've got. So dBSPL equals 20 times the logarithm of x over 0.0002. Can you see that, puppy? Okay. 0 dBSPL equals 20 times the logarithm of some pressure x over 0.0002. Because 0.0002, that's the ground. That's holy. That's 0 dBSPL. So what if you had a pressure of 0.002? Not 0.0002, but 0.002. What's that dBSPL? First you do the fraction. 0.002 divided by 0.0002. So I'll write it down here. First you do that. Once you did that, if you did the division, you'd end up with, I think it would be 10. What's the logarithm of 10? How many times does 10 have to be multiplied by itself to equal 10? Once. 10 times 1 is 10. Okay. And now you do 20 times that logarithm. If that logarithm happens to be 1, because 10, the logarithm of 10 is 1, 20 times 1 is 20. So 0.002 dynes per centimeter squared equals 20 dBSPL. Let's pick another one, 0.02 over 0.002. Let's say you had that pressure against the eardrum instead of this one. So 0.02. Get your calculator. 0.02 divided by 0.0002 equals 100. What's the logarithm of 100? How many times does 10 have to be multiplied by 10 to equal 100? Twice. 10 times 10 is 100. So the logarithm of 100 is 2. What's 20 times 2? 40. There you go. 40 dBSPL. Done. Okay? What happens if you had a pressure of 4 zeros in front of the 2? 0.00002. That's even smaller. than 0.0002. Don't need to do any math. You just figure it out. If 0.0002 was 20 dB, 0.00002 would be minus 20. Don't even need to do the math. As soon as you add an extra zero in front, so every time you increase the pressure by a factor of 10, you go up 20 dB. Every time you decrease the pressure by a factor of 10, you go down 20 dB. That's the secret. There's no math involved. Keep it simple. Slane and Pimple. Okay? Good. I see a smile on her face. I'm glad. That's good. All right. So always remember, too, to look at your little decibel section in your units. And when you're looking at the units and these notes, I always say FNO, freak not out. Look at the bold-faced heading and then read the crap underneath it. Okay? It's like, don't make it all this great big jumble of, oh my God. When you eat your supper, you don't take your plate and slam it in your face. You take a fork and you take a bite. So every time you see a bold-faced heading and then the writing underneath, that's one gobble. That's one forkful. And make sure you got that forkful. And then go to the next one. And that's how I arrange the notes, just very carefully. So in your dB Unit 2 section, you will run into, I think it's on page 3 or something, maybe page 4, and you're going to talk about dB versus dB SPL. Remember that? dB versus decibels sound pressure level. And when you relate this to hearing aids, and you're going to study this more next year in your year 2, okay? Input to the hearing aid, the sound coming from the room into the microphone of the hearing aid is always measured in dB SPL. It might be 20 dB SPL, might be 60 dB SPL, whatever the hell SPL, okay? Then the hearing aid adds pressure. The hearing aid is amplifying. And what the hearing aid is adding is called gain. And gain is relative. You can add 50 dB of gain, for example, to a 10 dB SPL input. You can add 50 dB of gain to a 5 dB SPL input. You can add 50 dB of gain to a 50 dB SPL input. Okay? And when you're adding an SPL and a dB together, you can, C-A-N, can add them like 1 plus 2 is 3. Okay? But you can't add 2 dB SPLs together like that. Both of them are referenced to the ground. So if a machine is making 90 dB SPL and you put another machine beside it making 90 dB SPL, the sum total isn't 180. Okay? It's going to be 93. And what's the gain that you had there? 3. Because 90 plus 3 is 93. Okay? So gain is always measured in dB. Input is always measured in dB SPL. Output from the hearing aid, the sum total of input plus gain, is also measured in dB SPL. Okay? So dB SPL is always some decibel value referenced to the ground. dB is a relative decibel value. And think about time. Okay? I'm on Pacific Standard Time. You're on Central Time, I think. Are you both in Missouri? I have no idea. Okay? Where are you?
Me?
Where are you located?
I'm in Vermont, so I'm on Eastern.
There you go. You're in Vermont, Green Mountain.
Yeah.
Yeah, you're on Eastern Standard Time. Sure. So that's your ground. That's your reference. So if it's right now 6:15 my time, it's 9:15 your time. Okay? So that's your ground. But if I say 2 hours, that's a relative time value. I can add 2 hours to my time. I could add 2 hours to your time. 2 hours is a relative time value. So when you think of 2 hours, think of gain in a hearing aid. Gain is what a hearing aid is adding to the input. And gain is a relative value, and you can add it like 1 plus 2 is 3. And thank God we can do that in our field, because that's what we do, is we fit hearing aids. We're not testing the sound pressure level of machines in a factory, okay? Because that's when you're adding a dBSPL and a dBSPL together. And then you cannot add them like 1 + 2 is 3. All right, next, Unit 3. And Unit 3 deals with complex sounds. And complex sounds are sounds that have more than one frequency. Duh, every sound in the world has that, except when you're listening under headphones for a hearing test. Okay? Otherwise, you're always hearing complex sounds. Traffic, noise, music, anything, talking. So complex sounds are often shown on a spectrum. And a spectrum is different from a waveform. A spectrum, remember what the axes represent. A spectrum, the axis represents frequency on the horizontal and dB on the vertical. And it could be dBSPL on the vertical. It could be dB. Who cares? Just call it intensity. Okay? Horizontal, it's frequency. And then you can see all kinds of individual frequencies on the spectrum. So a spectrum is not a waveform. A spectrum is a slice of a complex wave, and it shows you the individual frequency components in that sound. And what did we say that was so unique about speech? Speech is a complex sound, and it's got some tonality in it and some noises in it. And what does noise mean? What's the acoustics definition of noise? It's aperiodic. Remember that? Periodic and aperiodic. Periodic means the sound wave repeats over time. Aperiodic means you can't see any pattern at all. Noise is defined by sound that is not tonal. It's not, it's, okay? There's no tonality to noise. Noise is an aperiodic waveform that if you looked at it, it would just look like a jumble. You can't see any pattern to it. So speech is a unique combination of tonality, periodic sounds, and aperiodic noise. And when you think of vowels, A, E, I, O, and U, and you put your hand to your throat and you say any sound that vibrates the throat, that's tonal. G, B, D, even those consonants, B, B, D, M, N, I can always feel my throat vibrating. So they all have tonality in them. Same with vowels. A, U, E, E. Okay? But when you start going, I can't feel that vibrate. This isn't vibrating. This isn't vibrating. Those are pure noise. So unvoiced consonants are pure noise. Voiced consonants are part noise, part tonality. And vowels are pure tonality. They don't have noise. So when you're looking at the spectrum of speech, we won't draw individual lines, but we'll just say speech kind of goes down like this. It has a spectrum that has more energy in the lows and less amplitude in the highs. So vowels would be here, voiced consonants would be here, and unvoiced consonants like S, F, TH. And see, we focus on this because you're going to be fitting people with hearing aids. And what do they have most trouble hearing? What do they want to hear the most? Speech. So when you take an acoustics class, you got to know what speech is made out of. That's why we concentrate a whole unit on speech. And not the meaning of it, just the acoustics of speech. Just the raw acoustics. So if I say the word speech, the loudest part of that word is E. If I say church, the loudest part of that word is Okay, so vowels are loud, and low in frequency, and tonal. Consonants are soft, high-pitched, okay, and noise. And then I made people mix them together. I said, what if you have the letter T? Add a voice to it. D, d. Even feel where your tongue is in your mouth and say the letter T. T, t, t. Now make a D. D, d, d. Your tongue didn't move. Your tongue is exactly in the same spot. The only difference between a D and a T is that a D has a voice in it and a T doesn't have a voice. If I take the letter S, 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 now I say the letter Z. Z, 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 s, s, z, z. No change in where my tongue is in my mouth. It's just that one's unvoiced, the other one's voiced. Let's say I take the letter P. It's pure noise. If I put a voice in it, b, 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 Paul or Bob, I made them both with my lips. Nothing changed in the way I made it. It's just one had a voice, the other one did not. And that's what we focused on Unit 3. Okay, so know that combination of vowels, consonants, and then the mixture. So look at that area in Unit 3. Okay, good. Yeah, she's having a drink, so will I. Billy, it's good for the throat. All right, then you had a midterm exam. So all the stuff we've been talking about was pre-midterm. And I just wanted to focus on the most important elements to think about when you're studying for your final exam. On this review, it's those kind of questions that will be taken from before the midterm. Now we'll move past the midterm to more recent territory. Unit 4, Psychoacoustics. And in that unit, we looked at threshold. What's the softest it takes for you to just barely hear? And then we looked at a thing called bias. And we talked about things like method of limits, Houston-Westlake procedure, all this weird crap. Okay, so what did they do? You studied Unit 2, where you learned about the softest it took to just barely hear a tone. Okay. And that was sitting 1 meter in front of a speaker, listening with 2 ears. What happens if you play that same game with other frequencies? Not 1,000 hertz, now play it with 2,000 hertz. What's the softest it takes to hear 2,000 hertz at 1 meter distance from a speaker with 2 ears? What's the softest it takes to hear 4,000 hertz at 1 meter distance from a speaker with 2 ears? What's the softest it takes to hear 500 hertz at 1 meter distance from a speaker with 2 ears? And when people did that, they ended up with a curve. And the curve, this is going to be frequency here, and this is going to be dBSPL required to just barely hear all the different frequencies. So let's say at 1,000 hertz, okay, and then let's try 2,000 hertz. Oh, look, even less energy was required. Okay, so let's call 1,000 hertz. You will remember that was 0. We called that 0 dBSPL. 2,000 hertz can be heard at a little bit less than 0 dBSPL. Yep. 4,000 hertz, about the same as 0, or 1,000. And then 8,000 hertz, it takes a little bit more energy to just barely hear. And then 500 hertz, it takes more to hear. 250, it takes more to hear. So you can see that there's a sweet spot. And that sweet spot is because of the resonances of your outer ear. Oh yeah, be sure you know what the word resonance means. The favorite vibrating frequency of an object. And you learned in Unit 1 and in Unit 3 that resonance is determined by the mass and the stiffness of an object. The more mass an object has, the lower its resonant frequency. You can't jiggle a locomotive. Okay, just think about it in your head. You can't make a train go tick, 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 tick. Okay, massive objects hate being moved quickly. Whereas if you're holding something really stiff, it likes the okay, stiffness vibrates with highs. Lows resonate or vibrate with low frequencies. Mass vibrates with lows, stiffness vibrates with highs. So, because of the resonances of your outer ear canal and the resonances of your middle ear, that's why you got the curve. And what do we call that curve? MAF, minimal audible field. The softest it takes to hear all the different frequencies with one ear, I should say, with at 1 meter distance from a speaker with 2 ears. Okay, so let's make this book have 4 chapters. Chapter 1 was defining 0 dB SPL. And we did that in Unit 2. Chapter 2 is defining playing the same game at all the different frequencies instead of just at 1,000. That's minimal audible field. And then you'll say to yourself, Self, why do you care about that? Well, because you want to do a hearing test. Yeah, but we don't test hearing with both ears at the same time. Nope, we don't. We test hearing with one ear under a headphone and then this ear under a headphone. So let's find out what the softest it takes to hear all the different frequencies with one ear under a headphone. And when you do that, you get a second curve. And the second curve isn't quite as low as the first curve. It's a little bit higher because it takes a little bit more decibels to hear the sounds with only one ear as opposed to both ears. 2 ears are about 5 decibels better than 1. So the whole curve that you had at the bottom is just going to be raised up by about 5 dB. And that curve is chapter 3. And we call that MAP. MAP. The softest it takes to hear all the different frequencies with one ear under a headphone. And now we can take it all home and we can say, what's chapter 4? Chapter 4 is this. MAP is capital I, capital S, underline, bold-faced, italics, is 0 dB HL. So what's that on an audiogram? 0 dB HL. 0 dB HL is this. And we do that so that we can have a flat line instead of a curve. Who wants to say normal hearing is all different decibels across the frequencies? I don't. I'm too lazy for that crap. I'd rather call this whole curve a flat line. Always remember, though, the values of this curve are built into your audiometer. And the audiometer is what's used to test your hearing. So they build in MAP into the audiometer. And that's why your audiometers are calibrated every year. Just like you get a new sticker on your license plate every year or you'll get taken off the road, okay? You gotta pay up to the vehicle division of your state in order to keep your license plates. Same thing with an audiometer. Every year it's got to be calibrated so that 0 dB HL remains MAP. Because you can knock it out of calibration by bumping into it, by dropping the headphones by accident. So chapters, there's 4 chapters to the book. And it tells you the adventure taken to get to 0 dB HL, hearing level. So think of dB SPL as the ground for everything, and then think of 0 dB HL as the ground for the human race. That's us. That's human hearing. So the Unit 4 covered a lot of territory, okay? And then, so that's MAP, MAF, 0 dB HL. Remember the transitions. Boom, 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 boom. It's like a storybook with 4 chapters. And that's what chapter 1 is defining 0 dB SPL. Chapter 2 is defining MAF. Chapter 3 is defining MAP. And chapter 4 is calling MAP 0 dB HL on what's called the audiogram. The audiogram is the test upon which your hearing levels are placed. That's what it's for. So let's talk about that thing called threshold. A circle with a line through it. The Greek letter for TH. And they call that letter theta, T-H-E-T-A, theta. And it's a short word way of writing threshold. And what is threshold? The softest it takes to hear a tone. What's the softest it took for you to just barely hear 1,000 hertz? What's the softest it took for you to just barely hear 2,000 hertz? What's the softest it took for you to just barely hear all the different hertz? It really hurts. Okay, so threshold. It always ain't easy, because if you hear a sound and you think you hear it, let's draw the little boxes here. Now draw the boxes. I'm drawing like a little window here. See that? Good. Let's say the tone is present or the tone is absent. And you said yes or no. Okay, there's 2 things happening here. The tone can be presented or not presented, but the second thing that's happening is you're making a decision whether to raise your hand or not. So let's say you can hear down to 0. Let's say your hearing thresholds are 0 dB HL. For all the different frequencies, you could hear everything at 0. Perfectly normal hearing. Okay, so if you had that, and I was presenting the tones, all the tones at 50. Well, 50 is way more than 0. So every time you heard the 50, you'd be going, yup. And every time you didn't hear the 50, you'd be going, nope, I don't hear anything. As soon as I presented the 1,000 hertz tone at 50 again, yup. If I don't present the 1,000 hertz tone, I don't hear anything. So all of your answers are going to be here or here. Every time the tone was present, you're going to say yep. And every time the tone was absent, you're going to say nope. And that's what you call true positives, true negatives. Okay? When the tone was there, you said yep, true positive. When the tone was not there, you said nope, I don't hear anything, true negative. But now, how now, brown cow? Now let's make the sound 5 dB. Here, 5. Not 50 now. Now it's 5. Okay? Tone present, tone absent. You said yes or you said no. Same game, only instead of the tone being 50, now it's 5. Your whole attitude is going to change. Your eyes are going to change. You're going to be going, I think so. I think so. Your whole confidence is shattered because it's harder. the tone is softer. You can just barely hear it. It's so dang soft, you're not even sure whether you're guessing or not. That's what's going to happen to your clients in clinic. You're presenting the softest sound that they can hear. So they're going to be straining. They're going to say sometimes when the tone was present, they're going to say, yep. And sometimes when the tone was absent, they're going to say, nope. But also, sometimes when the tone was absent, they're going to say, yep. Wrong. False positive. They said yes, but the tone was absent. Or sometimes when the tone was present, they're not going to raise their hand. False negative. Okay? So now mistakes enter the picture. And when the sounds are soft, the devil, like smoke, comes under the door and into the room. And that's called bias. Bias is the difference between what you can hear and what you say you hear. Okay? So when the sound gets soft, bias enters the picture. You might have Herb or Mrs. McGillicuddy. Remember those two? Herb doesn't want to be at the test. Herb doesn't want to make a mistake. Herb's internal criteria are going to say, I'm going to only raise my hand when I'm sure I hear the tone. So if Herb can't hear until 50, you'd think 50 was going to be his threshold. Herb's going to wait till it's 60 before he raises his hand because he doesn't want to be anyone's fool and he doesn't want to make a mistake. Mrs. McGillicuddy, who used to teach first grade, she's the opposite. Her little white gloves on and her purse sitting on her lap. She loves tests. She used to give tests all the time. So she thinks it's great. She's just guessing. She's the Las Vegas gambler. And you're going, shoot, I didn't even touch the button yet. Okay, so Herb is going to give false negatives, and it's going to make the hearing loss look worse than it really is. And Mrs. McGillicuddy is going to be doing lots of false positives, raising her hand when the tone isn't even there. You're going to, if you're not good at doing hearing tests, her hearing is going to look better than what it really is. So that's what happens in hearing tests. You can go so far left, you've left America, or you can be so far right, your job is to pull them into the center. And that takes experience, and you'll learn it. Okay? All I'm there to tell you is when the going gets tough, the tough have to get going. When the sound is soft, you're going to make mistakes. You might err on the side of false positives, you might err on the side of false negatives, but either way, when the sounds are soft, that's when bias enters the picture. Good. Now, how do we test hearing? We use the method of limits. And what kind of threshold are we testing? Absolute threshold. Did you hear it or did you not? When you're hot, you're hot. When you're not, you're not. Okay? That's different from differential threshold. Differential threshold means you already hear the tone. What's the smallest change I needed to make for you to notice that there's a change? Okay? That's more for research. And we said people with sensory neural hearing loss, hair cell damage, their differential threshold gets worse. If they hear 1,000 hertz, if you make it 1,001 hertz, they won't be able to tell the difference. You'll probably have to make it like 1,020 hertz for them to notice the change in frequency. Because their hair cells are damaged and the keys on their piano are now wider. They've lost their frequency resolution. So their differential threshold for frequency is worse. Okay? But that's not what we're talking about here. That's called differential threshold, delta F with a triangle, okay, or just noticeable difference. What we're talking about here with Herb and Mrs. McGillicuddy is absolute threshold. Did you hear it or did you not? And what do we use to test absolute threshold? Method of limits. So put a star by that sucker, okay? Because that means two things. You, the clinician, are adjusting the tone, not the client, you are. And secondly, you're doing it in fixed increments. And our increments are 5. We don't test at 43. We'll hit 40 or 45. We don't mess with 41, 42, 43, or 44 decibels. We don't mess with that crap. Method of limits means two things. The clinician adjusts the intensity and frequency of the tones, and secondly, the clinician does so in fixed increments. And we do it in decibel increments of 5. Okay, how do we use method of limits? Do we go down, 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 down until the guy doesn't hear it anymore? Or do we start at 0 and go up, 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 up until the guy hears it? No, we use a combination. And that combination is descending and ascending. The Hewson-Westlake ascending, descending approach. So let's say you're testing Mr. Jones's hearing. You're going to come in at 70. He'll raise his hand. What will you do? Go down by 10. Present 60. He raises his hand. What do? Go down to 50. He raises his hand. What do? Go down to 40. He doesn't raise his hand. What do? Go up by 5 to 45. He doesn't raise his hand. Go up by 5 to 50. He raises his hand. So that's one ascending response at 50. You need 2 to define threshold. So you're going to descend by 10 again to 40. He doesn't hear it. Ascend by 5 to 45. He doesn't hear it. Ascend by 5 to 50, and he does hear it. Boom! That's threshold. 2 ascending responses at the same decibel level. That defines threshold. So again, this storybook has a couple of chapters. What are you looking at? Absolute threshold. How are you testing it? Method of limits. What version of method of limits are you using? Hewson-Westlake ascending, descending approach. Why do we do that? Because if we descended only, the guy would have better thresholds than if you ascended only. Because when you're descending, you know at least what you're listening for. You've heard the tone before. You're just dropping, dropping, dropping until you don't hear it anymore. But if you're ascending from 0, the guy has never heard the tone before. He doesn't know what to listen for. So we use a combination of descending and ascending. Hewson-Westlake ascending, descending approach to the method of limits. The last part of Unit 4 talked about binaural hearing. Why do we have 2 ears? So make sure you have a handle on that, okay? Main reason you have 2 ears, well, let's get rid of the first one. Binaural summation. Binaural summation means 2 ears are 5 dB better than 1. 2 ears are 5 dB better than 1. So if this ear can't hear until 10 dB, and this ear can't hear until 10, binaurally, if the tone is presented to both ears, I'll hear at 5. If this ear can't hear until 40, and this ear can't hear until 40, binaural presentation of the tone to both ears, my threshold will be 35. 2 ears are 5 dB better than 1. So never think that a one-eared person has a 50% hearing loss. He doesn't. Okay? Please don't ever mix that up because it's not true. The biggest reason, however, that you have 2 ears is to localize the direction of sound. All about the direction. And look in your notes and make sure you know, okay, that your ears are comparing the time of arrival to detect the direction of low frequency sounds, and they're detecting tiny intensity differences between the ears to localize high frequency sounds. So the little area in your brainstem called the superior Oliveri complexes, That's the first area to get info from both ears. And that little area is comparing the time of arrival of the sound and the intensity between the ears. So if I'm sitting here like this, and Julie spoke to me, her voice is going to hit my left ear a split second before my right ear. That's going to help me localize the direction of low frequency sounds of her voice. But if I'm sitting here like this and she's talking to me, the sound's going to be a little bit louder to this ear than it is to this ear, because my head is 10 pounds of ugly fat, and so I've got a head shadow between this ear and here. So your ears are detecting, or that area in your brainstem is detecting tiny intensity differences between the ears to localize the direction of highs, and tiny time differences between when they reach the ears to detect the direction of low frequency sounds. And the reason why you've got the two different cues is because low frequency waves are longer, and so they can wrap around my head. High frequency sounds are so short, they don't bend around objects. Highs bounce, lows bend, remember? So I have to use a different cue, because high frequency sounds are smaller, the wavelengths are smaller than the width of my head. So I can't use tiny time differences, because highs aren't going to bounce or bend around. I've got to rely on a different cue, and that cue is tiny intensity differences. And where does that change occur? Around 1500 hertz. Below 1500 hertz, you're looking at tiny time differences to localize the direction. Above 1500 hertz, you're looking at tiny intensity differences to localize the direction. Good. Unit 5. Here we go. We're getting closer to the end. Okay? Unit 5, you are talking about pitch and loudness. And we talked about loudness. Well, the bottom curve, you could call it MAF, you could call it MAP. Doesn't matter, whatever one you used. And FONs just show that all frequencies along one curve, look at MAF, for example, minimal audible field. All frequencies along that curve are heard equally loud. How loud? Just barely audible. That's how loud. Barely. At threshold. Okay? Let's say you played 1000 hertz now at 40 dB SPL. So now you're playing 1000 hertz at 40. So first I'll draw it. Here's MAF. All frequencies along this curve are heard equally loud. They're very different in intensity, totally different in intensity. That doesn't matter. To our perceptions, they're heard all the same, just barely audible. So they're heard all equally loud. Now let me turn 1000 hertz up to 40. I turned 1000 hertz now up to 40. Okay? And now let's do an experiment and find out what kind of curve would you get to make all sounds equally loud as that 1000 hertz tone at 40. So you said to the guy, memorize how loud that sounds. Now I'm going to play a 2000 hertz tone. You let me know when it sounds equally loud. Suppose he says there. Play a 4000 hertz tone, and you let me know when it sounds equally loud to that one. You might say here. Play a 500 hertz tone. Let me know when it sounds equally loud to this 1000 hertz tone at 40. You might end up here. Play a 250 hertz tone, and let me know when it sounds equally loud to that 40, and it might be here. So now let's draw the curve. There's your second curve. And that might be called 40 FONs. We'll call this one 0 FONs, MAF, because that's the loudness. We're not talking intensity now. We're just talking equal loudness contours. And here's their 40 FON curve. All frequencies along this curve are heard equally loud. How loud? As loud as the 1000 hertz tone at 40 dB SPL. They're all heard equally loud. And you could do that experiment at all different kinds of intensity. And the higher the intensity you go, the flatter the lines get. See, the bottom has a more deep curve. That one's less of a deep curve. This one's even less of a deep curve. Okay? And that shows you that these curves flatten out as the sounds become louder and louder. All sounds equally loud. Let's call this one 120. Well, if you matched all frequencies to that one, you'd find a fairly flat curve. And the differences are actually mostly in the lows, and that's why ghetto blasters or boom boxes have a loudness boost switch, because you need more energy in the lows to make them sound equally loud to the mids. And then you look at the thing called zones in that unit. Make sure you know what a zone is. And then in that unit, make sure you know what a mel is. And a mel is a unit of pitch as opposed to frequency. Loudness is the psychoacoustic perception of intensity. Pitch is the psychoacoustic perception of frequency. Okay, so the physicist talks intensity. What is the frequency? What is the intensity? And the artsy fart says, oh, what's the loudness of that pitch? Okay, all perception, subjective. And the scientist is objective, science, statistics. So intensity is physics. Loudness, your perception of intensity. Frequency, measured in hertz. Pitch, oh, does the musician have perfect pitch? So when you're explaining a hearing test to a client, don't use intensity and frequency. I would use loudness and pitch, because it means more to the average person. That's how average people talk. And when you talk to a client, it's always good to talk to a client at about an 8th grade level. Just common, everyday talk. Okay? Because that's the way you'll endear people to you. Anyway, that was mostly Unit 5. Unit 5 dealt with also frequency resolution. We revisited differential threshold again. We talked about different ways that pitch is represented in the body. And we said that the Helmholtz place theory, that's kind of almost getting toward anatomy again. Okay, high frequencies are represented at the base of the cochlea. Low frequencies are represented at the apex of the cochlea. Like keys on a piano, specific frequencies are represented in specific places. That's the place theory. And know the name of the person associated with the place theory. Helmholtz. Helmholtz. And then you had the temporal theory by Rutherford. And he said, nah, the place theory, nah. It's how many times the 8th nerve fires per second. Okay? That's what tells you what the frequency is. The only trouble is a nerve can't fire more than 500 times a second. So how do you tell what 1,000 hertz is? Oh, well, then one nerve fiber is going to fire at 500 times a second, and the nerve fiber beside it's going to fire at 2 times a second. So 2 times 5 is 1,000. So he gets into the volley theory. It's all part of the temporal theory. Well, why does that theory even exist? Because there's a couple of things that can't be explained by the place theory. And one of those is periodicity pitch. Remember that? A motorbike. Blah, 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 blah. And when the guy revs it, ring, da, 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 ring, Yamaha! Honda. How come when you make the da-da-da-da-da-da quicker, the pitch goes up? Each da-da-da is a burst of white noise. Da-da-da-da-da-da. So how come when they come out faster, your pitch perception goes up? That's not explained by the place theory of Helmholtz. That's better explained by the temporal theory. And that's why the temporal theory still has some grounding in it. Probably our pitch perception relies on both. Okay, the place theory and the temporal theory. They both likely play a part in how we detect the pitch of a sound. Unit 6. Unit 6 is the upward spread of masking. Now we're getting more recent. Okay, and the upward spread of masking has everything to do with anatomy. The upward spread of masking has everything to do with the shape of your traveling waves in the cochlea. Always remember that the envelope of the traveling wave in your cochlea is shaped like a kite. So if I was to roll out your cochlea with the base over here and the apex over here like so, so I rolled out your cochlea, uncurled it, and you got all the little hair cells standing in a row on your cochlea partition. Okay, there's your little hair cells. If I make a traveling wave occur in the low frequency region of the cochlea, low frequency hair cells near the apex are going to tell the brain you're hearing a low frequency sound. On the other, so when I draw the envelope of that wave, it's going to be shaped kind of like a kite. Okay? A steep front and a long slope going back toward the highs. Now let's say you have a peeping canary in your kitchen, and the canary is making a high frequency sound, and the traveling wave is staying right here at the base of the cochlea. Okay? And you have a rumbling truck outside on your street. The envelope of the rumbling truck can cover the peeping of the canary, and you won't hear the peeping of the canary. Now, it doesn't work the other way around. Let's say you have the soft rumbling of a truck outside your house. Okay? And Miss Canary is getting hairy in the kitchen, and she's freaking out, making a great big high frequency traveling wave. Guess what? That wave is never going to cover this. Okay? Lows mask highs better than highs mask lows. It's called the upward spread of masking. And what's low frequency? Background noise. What's high frequency? High frequency consonants of speech. So the upward spread of masking is going to wreak havoc with a lot of people wearing hearing aids. Okay? And you can't fight it. That's just the way it is. Lows mask highs better than highs mask lows. And background noise is the biggest complaint of hearing aid wearers. Huge complaint. Okay? And it's a big complaint even for normal hearing, let alone hearing loss. Upward spread of masking. And the other thing that's the fly in the ointment with hearing aids is loss of frequency resolution. A bigger delta F. People with hearing loss have poorer frequency resolution. They can't tell the difference between frequencies close together anymore. Your outer hair cells sharpen the peak of a traveling wave. Okay, they increase the frequency resolution. So now you hear that frequency, or you could tell the difference between this frequency, this one. You can tell the difference because the point, your traveling wave is turned into a point. And that's what outer hair cells do. If you lose outer hair cells, you've lost the point. So now I'll erase the point. And now you got a dull, rounded traveling wave again. So this guy, all these frequencies sound similar, okay? Because he's lost the point. And that's that's what reduces frequency resolution. So there are two things that screw up hearing aids: upward spread of masking and loss of frequency resolution. And this is covered big time in 120 anatomy as well. Be sure you concentrate on the physiology of the cochlea in unit 6, I believe, in anatomy. They're married. These two courses are connected. Okay? So loss of frequency resolution occurs because outer hair cells are damaged. When you've lost outer hair cells, your traveling waves are dull and rounded. So now, if the peak is like this, a whole bunch of frequencies are heard. You can't tell the difference between this frequency or this frequency, this one, this one, this one. But if the traveling wave is a point, now I can hear the difference between this frequency and this one, this frequency and this one and this one. I can hear the differences because my traveling waves are pointed. When you've lost the pointed traveling waves, they're all dull and rounded. Your hearing is sloppy. You've lost the ability. It's like the keys on your piano got wider. You've got, it's not as fine-tuned. Instead of having 10 fingers, now you're kind of like this. Okay? So you've lost the ability to distinguish between frequencies close together. That's why we keep talking about frequency resolution. Unit 6, upward spread of masking. Unit 5 talked about loss of frequency resolution. Okay, then we finished the course with Unit 7. Non-electronic acoustic modifications. The biggest one is venting. Always know venting. You've got venting to reduce the lows, filters to reduce the peaks in a frequency response, which are usually in the mid to highs, and then horns to increase the highs. Now, we don't use horns much anymore. Okay? We don't use filters much anymore. We did have to use those with analog hearing aids, but we don't much with digital. And that's what you're fitting. But we still need to use vents. So as an experiment, if you plug your ear with a hearing aid, and go ahead, stick your finger in your ear. And now talk, start humming. Hey, how are you? Give me a beer. Go ahead, talk, tell. There you go. Where are you hearing your voice? In the ear that's plugged. The occlusion effect. So if you have a hearing aid in your ear, you're going to hear your voice really loud in the ear where the hearing aid is in. It's going to really bug you. Okay? That's the second major complaint. Aside from background noise, the second one is the occlusion effect. So they put a hole in the hearing aid. And most hearing aids have it, a little hole in the piece that sticks in the ear. And that's to reduce the occlusion effect. And why does it work? Because it allows the volume of air trapped behind your hearing aid to communicate with the air outside the hearing aid. You've increased the acoustic mass of air. And lows are going to follow that mass because lows resonate with mass. They're going to follow that mass like Hansel and Gretel followed the breadcrumbs out of the forest. And the lows will escape out. Your occlusion effect will go away. Okay? So what is the occlusion effect in the lay definition? My own voice is louder when my ear is plugged. What did we say the professional definition of the occlusion effect is? 5 things. The book has 5 chapters. Here goes. Low frequency, bone-conducted sounds, because that's how you're hearing your own voice. You hear your voice through the air, but also through the bone. Okay? Low frequency, bone-conducted sounds resonate the mass of your skull, which in turn vibrates the cartilaginous portion of your ear, the part you can wiggle. 5, plugging your ear prevents that resonance from escaping. Got it? Be able to write it. That's a really important thing to remember. Low frequency bone conducted sounds resonate the mass of your skull, which in turn vibrates the cartilaginous portion. Plugging your ear prevents it from escaping. Well, if you put a hole in the hearing aid, it can escape. Okay? Venting. Big time. What's venting measured in? Millimeters diameter. Millimeters diameter. The bigger the vent, the more the lows go out. The smaller the vent, the less the lows go out. Venting is used in people who have good low frequency hearing. Because people who have good low frequency hearing will get the occlusion effect. Okay? If you don't have very good low-frequency hearing, you won't get low-frequency bone-conducted sounds being louder to the ear because you won't be able to hear them. The occlusion effect is a big deal for people who have good low-frequency hearing and poor high-frequency hearing. So if you've got someone with poor hearing in the highs but good hearing in the lows, thou shalt vent the hearing aid. Okay? And you'll learn way more about that in upcoming hearing aids courses. Well, we've been at this for an hour. Let me ask you, do you have any questions in particular that you find really difficult?
One of the questions from the midterm, I struggle with complex sounds for some reason. I'm not sure why,
Okay.
but complex sounds are just really hard for me to get. And one of the questions that I didn't get was fundamental frequencies in a complex sound is 500 hertz. Yeah. The next two harmonics are, I don't get that. What does that mean?
Harmonics are equal multiples of the fundamental.
Equal multiples of
Yep.
the fundamental.
Yep. So what's another multiple of 500 hertz? What's the next one? 1,000 hertz.
1,000.
What's the next one? 1,500 hertz.
Okay.
Good. No, I'm glad you asked that one. That's good.
Thank you.
Yep.
I think that's it. I don't know. Let
Yeah,
me
no,
take a
that's
look.
cool. We covered a lot of ground. We went through the whole ding-dong course, and I tried to lay out the important elements to make sure people have a sort of a sound grip on. And if you do, you'll whiz through it. You'll do just fine.
I think you answered a lot of my other questions that I had for tonight.
Okay, great. No, that's good. All righty.
Yep. Thank you.
No worries. This is all great. I can stop recording soon here then, and I'll upload it probably. I'll send an email out by Canvas and let you know where I'm uploading this review to. Not for you guys because you've been here, but for the people who weren't able to attend the review, I'll let them know where they can find this. I'll probably stick it in Unit 8 at the very end of the course, something like that. But you don't have to worry about it because you attended the review, so you're good for that. But this will just be for the people that weren't here. All right, in a slice. I wish you all good luck, as they say in French. Bonne chance. All right, have fun. Hey, I was just in the Netherlands. That was a trip.
I
You
bet.
ever been there? Holy cow.
No, but I'm from South Africa, so I know a little bit of the Dutch.
Oh, you do?
Yeah.
Ja, maar ik kon het Hollands verstaan. Niet zo goed.
Ja,
Een klein beetje.
Yeah.
I was practicing my Nederlands praten.
Oh, yeah. That sounds good, though.
Yeah, you've got the Afrikaans.
Afrikaans, yeah.
Where are you from? Kaapstad?
No, I was born in Zimbabwe, but I grew up in Johannesburg.
You grew up where?
In Johannesburg.
Oh, in Joburg. Okay.
Joburg.
I used to work for a hearing aid company, and I went to Johannesburg, Pretoria, Durban, and Cape Town.
Nice.
I went there a couple of times. That was neat. Anyway, all right. Dag. Tot ziens.
Thank you.
See you later. All righty.